Yeah, so I mean, I don't know, the discussion in the last class is not really, I mean, not a lot of it is not in the notes. Some of it is scattered in different places. But I kind of try to review this, just some basic, I mean, I didn't go into too much details because that will be take me too far away. So I just mentioned, I think most of the other things are there. The only thing which is not there here, I think, is the ratio test. No, that is not mentioned in this notes in this book. But other things like Cauchy criterion, etc., they are there. The only thing is ratio test. I mentioned ratio test because that's the easiest way of checking. I mean, if your series is given, the easiest way to check is a ratio test. No? And just to remind you, so if you have a series something like sum over Fn, okay, n going from 1 to infinity, then you can look at the ratio, define Wn is equal to say Fn plus 1 divided by Fn. This works, of course, assuming that all the Fn's are not 0. Otherwise, you cannot divide. No? So, assuming that none of these Fn's are 0, you can construct this object. Okay. And if Wn is less than some number L, which itself is strictly less than 1, if say Wn is less than or equal to some number L, which is strictly less than 1, then that proves then it means that this series is convergent. Notice that it's crucial that this L must be strictly less than 1. If you had just a condition Wn, suppose if L was equal to 1, then you would have something like this condition, right? But this is not enough, because as you saw already, the harmonic series 1 over n summed over n from 1 to infinity, this is not convergent, right? We saw that, right? This was not convergent, this was diverging. This was going to infinity, right? It blows up as you take the full sum. However, if you just compute the ratio, so Fn plus 1 is 1 over n plus 1 divided by 1 over n. This is the Wn, which is n divided by n plus 1, which is certainly less than 1 for any finite n, right? Of course, in the n goes to infinity limit, this becomes 1. But for any finite n, it's less than 1. So in that case, this would be this situation where L is 1, yeah, and this is not convergent. So this test fails, I mean this ratio test fails if this L was equal to 1, okay, then you cannot conclude anything. The series may be convergent or may not be convergent. So here is an example where it's not convergent, but if you take this example 1 over n square, right, this we know is convergent. I didn't prove to you this is convergent, but just use the same method that I used to prove that this was divergent. You can use the same method to prove that this is convergent. I didn't show that, but it's okay. But you see that here again, if you compute Wn, it is 1 over n plus 1 square divided by 1 over n square, which is n square divided by n plus 1 square, which again is less than 1. I mean, less than or equal to 1, let's say, because if n goes to infinity limit, it becomes equal to 1, right? So here you see it's again this capital L is 1 for this, but this is convergent. So for L equal to 1, it can happen either way. We cannot say anything more. You have to examine more closely the given series. But if L is 1 less than 1, then it is for sure it's convergent. And it's a very useful test. Many things. Another thing, you remember yesterday, I mean last time I also mentioned to you the uniform convergence. How if it is uniform convergence, then you can exchange the limit n going to infinity limit and the integrals, right? You can exchange. And the example I gave you to show that it is not possible if it is not uniformly convergent was this example where I considered a sequence of, not series, but sequence of functions, which was nx times e to the minus nx squared, right? Where n is, so this is Fn, let's say. This is a sequence. And of course, in the n goes to infinity limit, so this and the n goes to infinity limit, Fn goes to 0, right? Because I mean this exponential suppression can go for any finite x. X was between 0 and you could choose any upper limit, infinity or 1, or it doesn't matter, whatever limit you choose. fn goes to 0, right, for large n goes to infinite limit. However, we saw that if you take the integral, so in other words, what we are saying is that fn, the sequence, goes to f, where f is simply f of x. I mean, these are all functions of x, where f of x is simply 0, right? That is what we are saying. So now, if you do an integral of f of x from 0 to whatever that number is, I don't know, let's call it something a, okay, 0 to a dx, this will be 0, right? Because of course f of x is 0. However, we saw that if you take the integrals of fn x from 0 to a dx, then this doesn't converge to 0. This integral doesn't converge to 0. Okay. Actually, the main problem for this, the main problem here is actually the lower limit 0. Okay. Suppose that you had, I mean, you see that really the problem with the non-uniform convergence is coming because 0 is I mean, this x can go as close to 0 as you wish. That's the reason why this is happening, right? I mean, if you try to plot this function, so what happens? So you see that at x equal to 0, of course, this function is 0. So if I try to plot x and fn x, try to plot that. At x equal to 0, it is 0. But then if you look at the slope, what is the slope of this at x equal to 0? That you can just obtain by taking derivative, right, with respect to x, and then set x equal to 0 to find the slope, right? So obviously, to get something non-zero, this derivative should act there, right? When derivative acts there, you just get n times this quantity, but this quantity is 1 at x equal to 0. So slope is n. So the slope is going like this. So as you see that as the n increases, the slope will become bigger and bigger. The slope is n. So in other words, tan of this angle is n, right? That is the slope. But then, of course, as you increase the x, this exponential suppression will be dominant compared to this linear growth, right? So for large values of x, it will go to 0. Okay, huh? So this is going to be like this here. It sort of goes like that, and then it goes like this. This is the beta function. Huh? In fact, more or less the maximum value, you can see what it is. I mean, I think you can see how much it can grow by just choosing x equal to 1 over root n, for example, right? If you choose x equal to 1 over root n, this becomes e to the minus 1, which is some definite number, some fixed number. But this becomes root n, because x is 1 over root n, so it's a root n, right? So this more or less goes up to, say, root n times some number. That number which is e to the minus 1. But it grows like square root of n, right? The maximum value will keep increasing as you increase the n. But this will start becoming sharper and sharper, right? So as you increase the n, first of all, the slope here increases. So the picture will be like this. It will keep going like that. For any finite value of x, if you take sufficiently large n, here you can make it arbitrarily small by taking large n. Problem happens here in this very, very close to 0. That's where the problem happens, because as you increase the n, this becomes larger and larger, right? But the thickness becomes small. Right? That is the way it's happening. So if you had actually not taken this range, but let's say some a to b, okay, where a is greater than 0, strictly greater than 0. Okay. In that case, there will be no problem. These two limits will, these two operations will commute. Okay. You can, I mean, so instead of this, suppose I have taken a to b, then there will be no problem. You will see that this integral also goes to 0 as n goes to infinity. Okay. So long as a is strictly greater than 0. So the entire problem is appearing at that. This is where the uniform convergence breaks down, near x equal to 0. Everywhere else you can have, if it was the range was from a to b, then you can show that inside this range is uniformly convergent. This sequence is uniformly convergent. Okay, that's why you can commute. I mean, so there's no contradiction with that. The fact that you can, these two operations commute. Okay. So, now let me go back to the Taylor series now. So, I think there are 2 or 3, I mean at least another more property of series I will need, but I will do it when I will need it. Okay? When I will discuss that property of the series when I will need it. Okay? So, first now let me proceed with the Taylor series. Yeah. Where is it? Yeah. So, the statement is the following. That is a Taylor series, a theorem. And it says that if a function f, if there is a function f of z, which is analytic, so let me draw the picture instead of saying this. So, here is some point z naught, let us say, and I consider some circle, and let us suppose that this function is analytic within this circle, which I call gamma. Okay? So, in this entire region, I assume that this function is analytic. Okay? So, this function is analytic in this region, in R, as well as of course on the boundary also, and gamma. Not just the interior of the thing, but also on gamma. So, in this entire thing, it is analytic, and this circle is, I mean, what is z naught? Z naught is the center of the circle. The circle has a center. So, it takes z naught to be the center of the circle. Then the statement is that, so in other words, f of z, so if I take any z in the interior or even in the boundary, then this function f of z is analytic. That is our assumption. Okay? Then this f of z can be expanded in the following way: a n z minus z0 to the power of n, okay, summed, n going from 0 to infinity, where a n has a very definite thing, which is 1 over 2 pi I f z prime minus z0 to the power of n plus 1 dz prime integrated over gamma. Okay. So, I will always choose the path counterclockwise. So, this is the path, I mean, because you have to specify, when you specify the contour, you have to also specify the direction in which you are integrating. So, I will always choose it to be counterclockwise. So, this is the direction. Okay. Right. So, this here is, you see, it's a series, and the statement is that you can write f of z is in this form. This is an infinite series, but this series is in fact convergent. Okay. This will be convergent, and in fact it will be even uniformly convergent. So, uniformly convergent in this, inside this, in this region. I mean, z can be anywhere, and it's uniformly convergent. Okay. So how do you prove that? The proof is that starting from the integral representation. Remember, that was a Cauchy integral representation for a function, for f of z. So, integral representation was f of z is equal to f of z prime dz prime over z prime minus z integral, say, over gamma 1 over 2 pi I. Right? This we already saw this integral representation two lectures back, 2 or 3 lectures back. We saw that. Okay. Now, let us write the 1 over z prime minus z as 1 over z prime minus z naught plus minus z minus z naught. Okay. I can do that. Where you remember, what is z prime? Z prime is on the contour. So, in this particular case, the contour is, remember, a circle centered at z naught with some radius, let us say r. Let us say r is the radius. So, okay. So, I write like this, and now you see that z prime is some point here on the circle. So z prime minus z naught is, of course, the length of this is r, whereas if you take z minus z naught, which is this length, because remember z is in the interior, okay. So z minus z naught, this length is going to be smaller than that length, right. So absolute value of this quantity will be less than the absolute value of that quantity. So let me take out 1 over z prime minus z naught as a common factor, and then I write it as 1 minus z minus z naught divided by z prime minus z naught. Okay. You see, this is some quantity whose absolute value is less than 1, right, because absolute value of z minus z naught is the length of that thing, which is less than absolute value of this, right. So this absolute value is less than 1, and then I can do expand. I can expand it. There is geometric series, right. So I expand this. So I'll get here 1 over z prime minus z naught sum n equal to 0 to infinity z minus z naught divided by z prime minus z naught to the power of n, right. And this, as we already saw, this is a convergent expression. This series is convergent, right. It's convergent because z minus z0 z naught divided by z prime minus z naught is less than 1. For this reason, I can do this, I can make this, I can expand it. Okay, so let's substitute that here. So what we'll find is, so let's see, sorry, this z minus z to the power of n, this to the whole to the power of n. Okay. So now I substitute that and use the fact that z minus z0 z naught does not depend on z prime, so I can take it out of the integral. So you find here, so 1 over 2 pi I times z minus z naught to the power of n. I mean, there is a sum n equal to 0 to infinity. There is this, and then I have the integral f of z prime minus z to the power of n plus 1 dz prime. So let me put 1 over 2 pi I here. This one, yeah. It's just I made an expansion of this. Remember, we saw that 1 over 1 minus x is the same as 1 plus x square, right? Provided x is less than 1. So just take this to be the x, this whole thing to be the x. Its modulus is less than 1, so we can expand this. We can expand this. So that's what I did. And then I substituted that here. This is 1 over z prime minus z, right? So when I substitute and then I have to integrate it, all I did was I took this z minus z0 to the n outside the integral, because this depends on z prime. The integral variable is z prime. There is no z prime inside, so I took that out. And then the remaining part I just leave it as it is. So 1 over 2 pi I integral over f z prime time divided by, there is z prime minus z0 to the n here, but there is also one factor outside. So that makes it to the power of z naught, sorry, z naught to the power of n plus 1. Yeah. Yeah. So this is exactly what we wanted to prove. You see, we are saying that fz can be written in this form, right, in this series, where an is this coefficient, okay? But that's exactly what it is here. This is the an, right? This whole thing is the an. So that gives the proof. I should say that perhaps maybe at this point I must mention something. You see, the issue of, I mean, here I did exchange the integral inside the sum, right? Because remember, I mean, this was the just 1 over z prime minus z is this. Integral is outside, but I exchange the integral and the sum, which would be okay if this was uniformly convergent expression, right? So we just need to check that if it's uniformly convergent, and for that I'll prove some statement which is this is a general statement here, that for a power series, this is called power series, by the way. Power series, I mean, in general, a series would be this f and z, sum over n going from whatever 0 to infinity, right? This would be a generic series. But a power series is something where the f and z is some power of z minus some number, like here, z minus some number, z minus z naught to the power of n. So in the special case where you have z minus z naught to the n times some coefficient a n, okay, and you look at this series n equal to 0 to infinity, this is called a power series because it's the powers of this z minus z naught. So each term in this the nth function is simply z minus z naught to the n. Okay? So it's a special case of a series. For this case, for this power series, what you can prove is that if this series converges at for some z at some value of z, then let's call it at some value z equal to say z1, not z, let's call it something z equal to z prime. Suppose this, when I compute this thing at z equal to z prime, suppose it converges. Okay? Then what we are saying, then this series converges for all z inside the circle I mean z minus z naught is less than z prime minus z naught. Okay. In the disk, let's say inside the disk, and uniformly. This is a general statement. Okay. So that immediately shows that, right? Maybe I shouldn't use z prime. I mean some z double prime, not to confuse with the z prime there. Okay, I will not use so z double prime. So you see, we know that this series converges for any z which is less than z prime. So choose some z double prime such that it's inside here, some z double prime. It converges. This geometric series converges, right? Because its magnitude, I mean this length is less than that length. So ratio is less than 1. So it converges, right? But then what this theorem is saying is that then it is uniformly convergent everywhere inside. That's so therefore, I mean if you accept this for the moment, if you accept this statement for the moment, then we see that this is uniformly convergent, and then it's legal to exchange the limits. Okay, and of course this series is convergent by definition. Because that's I mean every step in the intermediate step is convergent, right? So the statement that I can commute these two operations, again I will get a convergent answer, right? So it's a convergent thing, but again at the end of the day, after having done all that, what I'm getting a power series z minus z0 to the n times this quantity, which is some an, some number an. So it's again a power series. Okay. So again by the same statement, this power series will be uniformly convergent in the entire disk. Okay, so that means Taylor series is uniformly convergent in that inside in this disk. So main thing to check is this statement. To prove the statement, so let's do the following here. So let's suppose this z double prime is some point. I just choose any point. I mean the inside of the thing. And let's say this radius is something. I use already this r, something else. Let's say, what shall I use? R double prime. Okay. So I use this length r double prime. Now the statement, I mean the fact that, so what we are given is that when z equal to z double prime, this is convergent. This series is convergent, right? So we are saying that a n z double prime minus z0 to the n converges. Right? This is what is given to us. But then by using Cauchy criterion, you see, Cauchy criterion, remember, is that for any epsilon greater than 0, you can find there exists some n which depends on epsilon, such that this sum k equal to n to m, where I take m to be greater than n, of these coefficients a n z double prime minus z 0 k a k a k. This is going to be less than epsilon whenever for all n and m greater than capital N. Right? This is a Cauchy criterion. Right? Remember, we did that. I mean, Cauchy criterion initially I mentioned to you in the sense of sequence, but you can convert it back here, because sequence from here you can construct a sequence by taking partial sums, right? And then the difference between the two elements of the sequence is simply a sum between some definite range from n to m, right? Where this n and m are greater than this capital N epsilon. In particular, I mean, this is true for all n and m greater than capital N, of course subject to m greater than n, otherwise this doesn't make sense. Okay. So in particular, now to look at m equal to n plus 1, I mean this should be true for everything, so let's take m equal to n plus 1. Okay. When m equal to n plus 1, maybe I should write it as, yeah, okay. No, maybe I should write it like this. Actually, m is greater than or equal to n. In fact, the reason is the following. Maybe I skipped one step, so let me just go through that. Remember, what was the step here? Is that we wrote some partial sums, Sn. Partial sums was this thing ak z minus z0 to the k, z double prime minus z0 to the k going from 0 to n. This is the partial sum. Okay, and then I can so then the Cauchy criterion was we have Sm minus Sm was less than epsilon for all m and n greater than capital N epsilon. Right? That was the statement. So now let's take m equal to n plus 1. Okay, choose m equal to n plus 1. Then what's going to happen when you take the difference between these two? So what is Sm? Sm is just the same thing from k equal to 0 to m, right? But if you take m equal to n plus 1, this will be 0 to n plus 1. When I take the difference, everything will cancel except the last term, the n plus 1th term, right? So in this case, Sn plus 1 minus Sn is simply a n plus 1 z double prime minus z0 to the power of n plus 1. Right? So what we are saying, the Cauchy criterion is saying that this must be less than epsilon, right? Okay. For any epsilon, no matter how small. That means these individual terms in the limit n goes to infinity must vanish, must go to 0, right? Because you can make it arbitrarily small if you choose sufficiently large n. Okay. So so for any convergent series, this is necessary condition. It's not a sufficient condition, but it's necessary condition that these terms must go to 0 as n goes to infinity. Right? This is necessary. Otherwise, the series will be divergent. Okay? So it's a necessary condition, but not sufficient. It's not sufficient because, as we saw already in the harmonic series, this 1 over n. Right? I mean, these terms are going to 0. Individual terms are going to 0 at infinity, but we know that this is divergent. So this is not a sufficient condition, but it's a necessary condition. Okay. So that means that all these terms are bounded, right? Because anyway, for any finite value of n, all these are bounded. These are some, I mean, each term is some finite number. Okay. And also we are saying as n goes to infinity, this is all going to vanish. So each of these terms is bounded by some number, right? Some finite number. Okay. So let's say I mean, so let me say that. So this implies, this criterion implies, choosing m equal to n plus 1, that a n z double prime minus z0 to the power of n go to 0 as n goes to infinity, right? This is what it is saying, each term. Okay. So this in turn implies that all of these terms, a n z double prime minus z0 to the n modulus is less than some finite number a, is bounded by some finite number a. Right? Because I mean, see, for every finite value of n, this is some finite number, right? The only way this could have violated this, that it's less than some finite number, is if this in the n going to infinity limit, it was becoming larger and larger and larger. So then it will be have no bound, right? But we have already shown that is not the case. In fact, n goes to infinity, it goes to 0. Right? So certainly this is true, that there must be some, maybe no matter how large, but some number, some finite number, and this is all bounded. Okay. So that means now remember z double prime minus z. So this mod is the same. I mean this implies it's a n modulus times the modulus of that, which is r double prime. That's the length. Huh? So it's r double prime to the n is less than for every n, for all n. That's the conclusion. Okay, so this is an intermediate step, but remember our aim is to show that this series is uniformly convergent. We want to show that this series is now z minus z0 to the n summed n. This is uniformly convergent. Okay, so let's do the following. So let's write it in the let me see. Yeah, so let me try to see what is it here. Let me just multiply and divide. Huh? So in fact, what I will do is I will just take the absolute value of this quantity, okay? And so this is going to be less than or equal to absolute values of individual terms, z minus z0 absolute value to the n summed over n. Okay. Now let me multiply and divide by r double prime to the n. Okay. But then use the fact that a n times r double prime to the n is less than this capital A. So this I can write it as less than n going from 0 to infinity. Capital A, you see this does not depend on n, so I can take it out. Okay. And then what is left over is simply z minus z0 to the power of n divided by r double prime to the n. So in fact, so let me look at the following. So what we want to do is look at the Cauchy criterion. So let's take from, let me put here k equal to n, some n to m. Okay, and we want to show that this is like, I can make it arbitrarily small. Okay, that's what I want to check. So in this case, this will be from k equal to n to m. This is k, and here I then use this thing, and then this becomes k from k equal to n to m. Okay. We want to show that this you can make it arbitrarily small by choosing some capital N which does not depend on z. That's what we want to show, right? Okay. So what is this? This sum you can explicitly work out. Well, this is nothing else. I mean, this guy, this object is, so in other words, this whole thing is less than, so z minus z0 divided by r double prime to the n. Okay, that is going to be common factor in each of these terms, right? Okay. And then what is that? After that will be 1 plus z minus z0 divided by r double prime plus this thing square, I mean this thing square, all the way up to this thing to the power of m minus n, right? Okay. I mean, I'm just not writing. This is the same thing inside. This is a notation instead of writing it again and again. So, so what do we get here? But this quantity is same as, so z minus z0 over r double prime to the n, and then this is simply, this we explicitly worked out, right? 1 minus z minus z0 over r double prime to the power of m minus n plus 1 divided by 1 minus z minus z0 to the power of r double prime. Okay? Remember, this is how we actually we proved that the geometric series is convergent. Okay? This you can sum, right? You remember this the way we did. Huh? I mean, if you have 1 plus x up to some x to the k, then you remember what we did. Let's call it some q. Q is equal to that. Then we just multiplied x cube. You get here x plus x square all the way up to x to the k plus 1, and take the difference between the two. So you get here 1 minus x times q, but here the difference is all this x square, etc. cancel, and you're just left with the 1 minus the last one, x to the k plus 1. So 1 minus x times q is 1 minus x to the k plus 1. So q is that divided by this. This was it. Okay. And now this is immediately obvious. You can make this arbitrarily small for sufficiently large n, right? So this is going to be less than 1. Okay. So if you wish, you can choose, I mean, z double prime, choose another point, which is a little less than z double prime. So if you take any disk around it, which is a little less than z double prime, then this quantity is certainly less than 1, right? I mean, so less than that number, this ratio, right, which is less than 1. Okay. So you can go to sufficiently large n, independent of the z, independent of where the z is inside. Okay. And you can make this arbitrarily small. Okay. That's the idea. Okay. So I mean, this quantity z minus z0 divided by r double prime to the n can be made arbitrarily small. Arbitrarily small for n large. But the important point is the largeness of n. I can choose independent of z. This is where the uniformity comes, right? I mean, this is true for any convergent, but the statement is that I mean, n greater than or equal to some capital N, where capital N does not depend on z. Okay. I mean, you can, yeah, is that point clear? Last point, is this point clear? I mean, I'm saying that to choose something else. I mean, choose something, I don't know, now I'm running out of the indices, another point which is a little bit closer to z naught compared to z double prime. Okay. So call that, so this radius will be something, r, capital R, let me call it capital R, although I'm using capital R for this region, but this is, I'm just, because I'm running out of indices, r and r double primes. Okay. So if I choose capital R, then you see any z minus, so if z is inside this circle, inside this disk of radius capital R, okay, this value is going to be anyway less than capital R, the modulus of z minus z0, right? So it is sufficient to choose, the capital N such that R divided by R double prime to the power of n is less than epsilon. You see, is enough to do that. No matter what point z is inside is independent of that, because any point z which is inside this disk, for that this value is going to be even less than that. You see, so if this value is already less than epsilon, this value is going to be even less than that, right? And that's independent of the choice of z. Okay. I mean, this is the reason why there's a, for power series, it's uniformly convergent. If at some point, yeah, if it's, so that's the picture here, right? I mean, if at some point here it is convergent, then if you take z's inside, the value will be even less, right? That's the reason for this uniform convergence, for power series only. It doesn't happen for others. Because of the form z minus z0 to the n. So this is z0, and if I know that at some point it is convergent, right, then if I take anything inside, it will be only smaller. Absolute values will be even smaller than before, right? Because its length is smaller. This is the reason why it's uniformly convergent. Okay, so that was the point, Taylor series. Now, one more thing I wanted to say. No, this is okay. This I've already shown. Right. Okay. Any question on this? It's an important. I mean, you have seen Taylor series for the real functions and so on, right? But I mean, you have for one function of one variable you have seen, right? But there you have to, of course, assume that the derivatives exist to all orders and so on. But for analytic functions, we know the derivatives exist to any number, right? And furthermore, you can really make a very precise statement about the convergence. You see, it's convergent wherever. Okay, so let me just explain that a little bit. I mean, given any series, you can always ask the question, what is the radius of convergence, right? That is a question you can ask. So let's erase this. So given this series, Taylor series, so consider Taylor series. So Taylor series was f of z was a n z minus z0 to the n, where a n was 1 over 2 pi I, and the integral z prime minus z0 to the power of n plus 1 f of z prime dz prime on the circle gamma of, let me put here the radius r, radius r. This was a radius r, which was the original circle. So radius r centered around z0. Now, how big I can take this radius? I can take the radius as, I mean, what was after all the condition here? The condition was that function f must be analytic inside this disk, right? That was the only condition. So suppose that from z0, suppose the nearest singularity of the function is somewhere, let's say. Okay. Well, then you can take this gamma, the circle, as large as almost, I mean, very close to that point, right? And this series will be convergent in this entire disk. It will be convergent because instead of choosing this radius, you can choose that radius, right? And still the condition is satisfied that inside this disk there is no singularity, correct? So this expansion would be uniformly convergent if all, I mean, in the entire disk where you have taken a radius, I mean, which is just say, I mean, this point is outside, the singular point, nearest singular point is outside it, but you can go as close as you wish, not exactly passing to the singularity, but you can go as close as you wish. Okay. So this is what the radius of convergence is. So radius of convergence of this series, I mean, radius of convergence means how large can be z minus z0. That's the question. That's a so this is the statement is how large can z minus z0 be, okay, such that this series converges. And the answer to that question is from the z0 you look around and see what is the nearest singularity, okay, and you can choose z minus z0 to be just a little less than that nearest distance, and the series will be convergent inside this disk. Okay. I mean, as a simple example, the geometric series itself. I mean, if you take 1 over 1 minus z, right? This we know is 1 plus z square plus and so on and so forth. But this for z less than 1, this sums up to that. Right? But this has a singularity at z equal to 1, right? So I mean, remember here in this expansion, this is z minus z0, but I've taken z0 equal to 0. Right? It's the same type of expansion, except z0 equal to 0. So here is the picture here, 0, and this function has a pole there. Right? So indeed, we see that this has a radius of convergence where it's a circle of unit radius. Right? Anything little less than a unit radius, this is convergent there. If you take any point here, it's not convergent. This series is not convergent because absolute value of z is now greater than 1. So this series is simply not convergent.
So can we do this? Can we assume our origin line far away from the center?
Yeah, good. True. Sure. That will come into when we discuss analytic continuation. Yeah, in fact, that's a good point. I mean, so what happens? I mean, on the other hand, here I know this function is analytic,
yes,
right? Except that this series doesn't make sense.
Yeah.
So of course, here you can write another series, choosing some other. I mean, maybe some other other center, and so on. So this way you can actually keep enlarging. I mean, somewhere far away you go, then you can take a big circle out here. So like that. So you can analytically continue. So suppose I don't know this. I'm given that. Okay, in this case I could actually sum, no? But in many cases series you won't be able to sum and find out exactly what it is. But you suppose you know for some reason that whatever that series is well defined in some region, but it has some singularity somewhere else. No? And you can start extending it to other regions, no? By going through this analytic continuation. I will discuss that in some detail because that's a very important concept. I'll come to that later. Because there's a whole issue whether, I mean, maybe you analytically continue in one way and I analytically continue another way. Is that possible? No? The answer is no, it is unique. Okay? So that's why it's such an important concept. All right. So this was so far the Taylor series, and we also understood where, I mean, how far you can push it, how far you can push that series, right? And that is to the nearest singularity. Okay. Now let us consider Lorentz series. Yeah. There was a section 19 I'm not going to discuss because it's not much. I mean, it's just rewriting the Taylor series in the polar coordinates. So I will skip that. I mean, if you wish, you can look at it, but it's very straightforward. I mean, here it's written in the complex coordinate z minus z0, but here it is just expressed in the polar coordinates, the same expression. So that's not so important. I'll go to Lorentz series now. Yeah. So that's again, it's a very simple extension of the Taylor series. Sorry, one thing I forgot to mention. Remember the Taylor series we obtained was this expression fz was equal to an z minus z naught to the n, where an is 1 over 2 pi I integral z prime minus z naught to the n plus 1 fz prime dz prime over this gamma of the radius r, let's say. But this expression we already know what it is. The differential is a derivative of f at z naught, nth derivative of f, right? So this is the same as 1 over factorial n times dn f over dzn evaluated at z equal to z naught. Okay. This was, when we obtained the nth derivative, there was a factorial n there. So I just put that factorial down. So this is a standard Taylor expansion, right? This is what you do for one variable, exactly that. But except that here is much more powerful. You know the radius of convergence of it. No? Okay. So now the Laurent expansion. So the problem is the following. I mean, for Taylor expansion, I needed to have a Z0 and a disk of some radius, and a function had to be analytic in the entire interior of the disk, right? That was crucial for Taylor series, that it had to be analytic. But suppose it was not the case. Suppose the function was, I know that the function is not, I mean, suppose I am guaranteed that the function is analytic in this annular region. Maybe it has some singularity there, no? We don't know. But we suppose it's guaranteed to us, somehow it's given to us that it's analytic in this region. Here we don't know anything about it. Maybe analytic, maybe not analytic, but I don't know. Then in that case, again let me call this Z0, and here I have just two circles, inner circle and outer circle. Or let's say this some radius capital R and that is some radius small r. And we are guaranteed that in this region it's analytic. So now if I take Z some point here, can I write down some expansion? Taylor type expansion. It turns out the correct expansion there is expansion, and that expansion is called Laurent expansion. Okay, so we will discuss that. So how you will work it out? So maybe I should enlarge this thing. It will not be visible. I will just make it a bit bigger so that it's more clear. So here is my Z0, and here is the inner circle, and here is the outer circle. Okay, and Z is some point here. Let's say. Okay. So this is a gamma r with a radius r, and this is the gamma r small radius. Okay. So now let us consider the following a contour in the following way. You see, so let me see like this. So let's consider a contour which goes around like that. Okay. Then comes here and encircles this point Z. So point Z is say here. So it comes here and circles this point Z, then comes here. Okay. So this arrow is going like this, right? Arrow is going like that, arrow is going like this, arrow is going like that. Then it goes around this contour, but notice that this is counterclockwise, that is clockwise. So I have to remember that. There will be a minus sign if I want to write it as counterclockwise. Okay. Come around here, then go back like that, like that, like that, and then go around here. So and you come back here. Right? So consider this big contour. Okay. Now when I have drawn these two different lines, but actually they are on the same line. Okay. So which means the result of this integral will cancel the result of that integral because they have opposite orientation. Similarly, this will cancel that. Okay. So this whole contour, let me call it that big contour as C. So this big contour that we have drawn here is C, let's say. C. Then the integral over the C of anything is the same as integral over gamma r. Okay. Gamma r is in this with this orientation minus integral over gamma r. I put a minus here because this is clockwise. So if I want to write it again as a counterclockwise direction, then I have a minus sign. Okay. And then plus minus, let's call this little circle is gamma. Okay. Again, this is clockwise. So if I want to write it as counterclockwise, I'll have minus sign, minus gamma. Okay. So this is what we are finding. Okay. Now, if you now look at this contour C encircles what region? This region, right? So, but in this region, I am assuming that the function f is analytic, right? So if I integrate, so let's see. Now I should erase something. I can erase this part. So consider this integral f of z prime divided by z prime minus z, and integrate it on the big contour C. Okay. This is analytic everywhere, you see. I mean, because by assumption f is analytic in this region, right? And also z prime minus z is analytic in this region, because z is outside this region here. So z prime, I mean z prime minus z can never be 0, right. So 1 over z prime minus z will not have blow up anywhere, right. So this whole combination is analytic on this contour as well as in the region which this contour encircles. So therefore this integral must be vanishing by Cauchy theorem. Right? But on the other hand, this integral is the same as that. So what we are seeing is that this is the same as the integral of gamma r of the same quantity f z prime dz prime, dz prime z prime minus z minus the integral over gamma small r f z prime dz prime over z prime minus z, and then the integral over gamma minus the integral over gamma of f z prime dz prime over z prime minus z. But that is the same, I mean this is just this little circle. Remember this minus sign, I have taken into account the fact that this was originally clockwise. So now after putting the minus sign, it is counterclockwise, right. Then this is exactly the integral representation of the f, right. The integral representation for f at z, this is the point z, so is simply an integral over a circle, and of course f is analytic inside this region, right. So this integral is exactly the 1 over, I mean the 1 over 2 pi I of this is equal to f of z, right, because this little gamma is a small circle encircling the z. So therefore we come to this conclusion. Let's divide everything by 1 over 2 pi I, okay, to make it easier. I mean to 1 over 2 pi I, 1 over 2 pi I. Then this is nothing else but f of z. So now let me take it to the other side. Okay. So we find f of z is equal to 1 over 2 pi I integral f z prime dz prime z prime minus z over capital gamma r and minus 1 over 2 pi I integral over gamma small r in inner circle f z prime. Okay. Now this guy is exactly what we calculated before, right? Because after all, what we did, we wrote 1 over z prime minus z as equal to 1 over z prime minus z0 minus z minus z0. Then we took out 1 over z prime minus z0 as a common factor, and what is left over is 1 divided by 1 minus z minus z0 divided by z prime minus z0, right? And then we did the fact that you see z prime for the bigger circle, z prime is on here, right? So z prime minus z0 has this radius, capital R radius, whereas z minus z0 has smaller length. So this quantity has a absolute value less than 1. So we did an expansion, geometric expansion, and then we got what Taylor series was, right? Okay, so this I don't repeat again. That's exactly the same answer as before, right? So, okay, where shall I write now? Can I erase this part now? Because I don't want to. I erase it. But this, if I erase this, you will not. Okay, so I just remind you that this z is between the two circles, right? So I just write this down, that z minus z0 is greater than small r. Small r is this radius. Small r is this radius, and is less than capital R. This is what you need to remember from this picture. The small r is this radius, capital R is this big radius, and z minus z0 is this. So this is the only thing you need to remember from this picture now. Okay, so from the integral, the first integral simply just gives me. So let me call this first integral, and this is the second integral. So first integral simply gives me exactly like before. Just do the geometric series expansion of this, and you will get a n z minus z0 to the power of n, n going from 0 to infinity, where what is an? An is 1 over 2 pi I f z prime over z prime minus z naught to the power of n plus 1 dz prime. Okay. I don't want to write it as a nth derivative because I don't know. I erased the picture. I don't know whether it's analytic here inside. Right? I mean, it may or may not be analytic. So I just write it as integral. I don't write it as, right? Because z naught is inside the inner circle, and there we don't know whether it's analytic, right? So I'm not going to write it as a derivative. So that was the first integral. Now let's look at the second integral. Okay, again I do the same trick. I write 1 over z prime minus z as z prime minus z naught minus z minus z naught. This is fine. However, now you see z prime minus z naught has a length which is small r because it's in the inner circle. Right? So here z prime minus z naught is equal to small r. Okay, and we have the length of z minus z naught. This length is bigger than small r. So this time what I should do, I should take this as a common factor out. Yeah. So this becomes minus 1 over z minus z naught. Okay, minus because I take this out, and then what is left over is 1 divided by 1 minus z prime minus z naught divided by z minus z naught. Okay. And now this length is this is less than 1 because z prime minus z 0. So z prime minus z 0 divided by z minus z 0 absolute value is simply r divided by z minus z 0 absolute value, but it's in this z minus z 0 absolute value is greater than r. So this quantity is less than 1. Less than 1. So I can make a geometric series expansion. Okay. So what do we find this time? We find that this is the same as minus 1 over z minus z 0 and summed, let's say m z prime minus z 0 to the power of m divided by z minus z 0 to the power of m. Okay. Now plug that back in here and integrate z prime on the inner circle. So conclusion then is that this is going to give me, note that there is a minus sign here which cancels with that minus sign. Okay, it makes it plus. So you find that this is the same as I take out again z minus z 0 to power appropriate power because that's outside the integral, m plus 1, m going from 0 to infinity. So here's m is going from 0 to infinity, and then I have 1 over 2 pi I times z prime minus z 0 to the power of m times f of z prime dz prime. Okay. So this is some number. It's going to be some number. We can call it bm, some coefficient bm. Just like here we call it an. So call this as some bm. Huh? So this is the full series then. We are saying that the sum of these. So f of z is equal to this plus that, which is equal to that plus that. So you can just put them together and write a compact expression, well, I mean a uniform expression, which is f of z is equal to an, let me call it dn, not to confuse with that coefficient, z minus z 0 to the power of n, where now n going from minus infinity to plus infinity. You see, because here, you see these powers are negative powers of z minus z 0. Right? Here it's all n equal to 0, 1, 2. So z minus z 0 to 0, z minus z 0 to the 1, and so on. Right? But here, see, m starts from 0. So the first term is 1 over z minus z 0. Second will be 1 over z minus z 0 square, and so on and so forth. Right? So the result is that the range becomes from minus infinity to plus infinity, and those coefficients I call dn. So when n is, sorry, n, when n is non-negative, so 0, 1, etc., that dn is the same as that. Okay? And when n is negative, then it will be given by this. So in fact, there is a general expression for dn, which is simply that expression. F of z prime to the power of n plus 1 dz prime. this is the general expression because you see that for n non-negative, it's of course that expression. But when n is say -1, let's take n equal to -1, okay, then this disappears, and that's indeed the m equal to 0 term here, right? If you take m equal to 0 term, there is no z prime minus z0, right? And m equal to 0 is simply 1 over z minus z0, which corresponds to n equal to -1. So n equal to -1. Similarly, look at n equal to -2. N equal to -2 means 1 over z minus z0 square. That comes here when m is equal to 1, right? 1 over z minus z0 square, m equal to 1. But if m is equal to 1, this coefficient involves 1 power of z prime minus z0, which is the case here. If n equal to -2, this becomes -1, which goes up. So you can verify that this is indeed true for all the values. So it's the same type of expression, exactly the same formula even for the coefficients, except that now the range is from -infinity to +infinity, right? For Laurent expansion. Whereas Taylor expansion starts from 0 to infinity. That's the difference. Okay. And this you can evaluate in any contour, because any contour which is inside the annulus. Right? So on this contour, of course, this should be analytic. So you just evaluate on I mean, I shouldn't confuse with this big C. No, I mean any contour. I don't know, any contour inside annulus. Because it doesn't matter. I mean, even though this is this is evaluated for gamma r, this was evaluated for small gamma r, but it doesn't matter. I mean, you could push it, no? I mean, that picture was this. Here was a bigger circle, here was z0, and here was the inner circle. And anyway, the function f is analytic here. Right? So since function is analytic, also the z prime minus z0 to the n plus 1 is also analytic, because z prime is on this guy, on this z prime is not inside here, it's somewhere here, right? I mean here or there, and z0 is here, so this never blows up, right? Or if you take the positive powers again, they don't blow up. So this whole combination here is analytic in this entire region. So whether you integrate over this gamma r here, or you can deform it to any contour here, it doesn't matter, because right, that's the Cauchy theorem, consequence of Cauchy theorem, right? Because inside this whole place, the integrand is analytic. Similarly, whether you integrate over small gamma r, I mean gamma of small radius, or there, it doesn't matter. So all of these things you can evaluate on any contour, but the contour must be inside the annulus. That's the only condition. Okay. So any question on that, Taylor expansion? And the Laurent expansion? I mean, these equality signs are not completely, I mean, this was that part, but then I substituted that here. So this equality is for this. I mean, I hope it's clear. Any question? shall I proceed? Next points. Okay. So I think can I erase everything? I mean, it's all in the notes. This Lorentz series and so on. Okay. So now I want to define a few concepts. I mean, some definitions actually. So let's suppose again. Let's consider. So suppose at z naught, and consider the situation where this function f is analytic in this region, right? At z0 and some neighborhood of it. So suppose function f of z is analytic in a neighborhood of z naught. So then I can of course do Taylor expansion, right? And Taylor expansion was Taylor expansion basically gave fz equal to fz equal to z minus z0 to the power of n 1 over factorial n dn f over dzn evaluated at z naught, right? This was a Taylor expansion. Now, so I mean, it might happen that at z naught actually the function is 0. Could happen, right? And after all, a function could be 0 at z naught. So suppose that a function is z naught is 0. That of course means that the 0th term will vanish, right? But it could happen actually even the first derivative of the function vanishes at z naught, right? Or maybe the first few derivatives vanish. So it could happen. So it can happen. I mean, for special types of functions, it can happen that say f of z naught is 0, but also df by dz naught, dz at z naught is 0, and d2f by dz2 at z naught, all the way up to, let's say, some, let me not use n here, let me use m here. Okay. Let's suppose the first n, is it the first n, or let's see, or first n plus 1, first n minus 1. So first n minus 1 derivatives vanish at z naught, they are all 0, okay, but the next one does not vanish, is not equal to 0. Suppose that this is the case. Okay. In that case, you see, if you go back to the Taylor expansion, and what you find, so this would imply that a0 equal to a1 equal to all the way up to an minus 1, right? An minus 1, they are all 0, right? But an is not 0. But an is not 0, right? That's what you'll find. So this expansion f of z will start off. I mean, or first n minus 1 coefficients are 0, first n coefficients are 0. It will start from an, so it will be some an times z minus z0 to the power of n plus an plus 1 z minus z0 to the n plus 1 and so on, right? So there will be always z minus z0 to the n common to everything. So I can take it out. So you get write the z minus z0 to the power of n. I take it out as a common factor. Then you'll get here an plus 1 z minus z0 and so on. This is an infinite series which is again convergent, right? Because after all, what I've done, I've just taken out some factor, common factor out, but then the remaining thing is convergent. So that's also going to define to me an analytic function, right? So let's call this function as some h of z. This will be an analytic function. So the conclusion is that if a function behaves like this, it satisfies these conditions, then this function f of z can be written as z minus z0 to the power of n times another analytic function, right? Such that, I mean, this is an analytic function, but we also know a bit more, because we know an is not equal to 0. That means h of z0 is not 0, right? Because when z equal to z0, all these higher terms can vanish. Put z equal to z0, they all vanish, right? So what you are left with is an, but an is not 0. So we know that h at z0 is not 0. Okay. So this is the form. When something like that happens, you say this function has a let's see what is called nth order. Nth order 0 is called that function f has a nth order 0 at z equal to z naught. Okay. So that's a definition. If the function can be expressed as z minus z0 to the power of n times an analytic function, which is not vanishing at z naught, then you say this function has a nth order 0 at z equal to z naught. So then you say this function f has an nth order, it's a definition, order 0 at z equal to z naught. That's a main definition. That's one thing. See, one of the important property of this zeros of a relative function is that the zeros, I mean, if you look at the set of zeros, they will not have any accumulation point. Accumulation point meaning a limit point. If you take a sequence of zeros of an analytic function, they will not have a limit point. So limiting point was in the sense of if you have a sequence and if it converges to some point, that's a limit point. So in other words, I mean, suppose it had, I try to argue I try to explain what, suppose this function, suppose I find a function f, f of, let's say in real variables, for example. Okay. Then, and suppose I write it as x minus 1 over n product n equal to 1 to infinity. Okay. Consider a function like this. Now this function has a 0 at x equal to 1 over n, for any n integer, right? So it has zeros at all the values x equal to 1 over n for n belonging to, I mean, n equal to 1, 2, 3, all the way up to infinity, right? So these points, of course, have a limit point. They limit, if you consider the sequence of these points, 1 over n, it has a limit, and that is a 0, right? Which what it means, limit in the same sense, that given any epsilon greater than 0, I can find some element of the sequence, I mean, some capital N, which depends, of course, on epsilon. Let me call this xn, this nth 0, such that xn minus the limit point is 0, is less than epsilon for all n greater than capital N epsilon, in this sense. Okay? In the same sense that we define, which is indeed the case. I mean, all you need to do is to just take n equal to 1 over epsilon, or n greater than 1 over epsilon, right? Then you see this is obviously true. Yeah? Because 1 over n for n greater than, yeah, I mean, you see, you understand this is, I mean, this length will become smaller than 1 over epsilon, right? I'm sorry. How do you, I mean, is that clear to you, all of you, right? No? So what is this? This is 1 over n minus 0, which is, so 1 over n should be less than epsilon, we are saying, right? But this is the same, I take it on the other side. So this is the same as I multiply by n and divide by epsilon. So we are saying n is greater than 1 over epsilon. So if we just choose capital N equal to, say, 1 over epsilon, I mean the integer part of 1 over epsilon, because n, capital N is the integer, epsilon is the arbitrary real number. So integer part of it, and take any n greater than capital N, that's going to satisfy this condition. I mean, it should be intuitively clear, right? Because I mean, take the 0 here. 1 half, so n equal to 1 is 1, n equal to 2 is 1 half, n equal to 3 is 1/3, and you keep going. It's you see, you can come arbitrarily close to the origin, right? It comes closer and closer. In any distance, there will be infinite number of points inside of this type. If you take any finite length, finite distance away from 0, there will be infinite number of values 1 over n inside here, right? So this 0 is the limit. So this is when something like that happens, you say that this sequence has a limit point. And that limit point or accumulation point. So some people use the word accumulation point, some people use the word limit point. So accumulation, because it accumulates to there, it accumulates near 0. That's the reason why you say accumulation point. So if something like that happens, then you say that this function has zeros that have accumulation point. Okay? But you see, for analytic function, that can never happen, because now if you look at I mean, so we said if something has an nth order 0, this is going to be of this form, z minus z0 to the n times h of z, so that h of z naught is not 0, right? But by continuity, then in some neighborhood of z naught, h will not be vanishing, right? After all, it's continuous. If h of z0, say modulus of h of z0 was some number, not 0, some between some finite number, let's say even 0.1, let's say, right? Then by continuity, there will be some small neighborhood where h of z will not be vanishing, right? And if that will not vanish, but also z minus z0 to the n also will not vanish away from z0 in that neighborhood, right? So you can find a neighborhood around z naught where it has no other 0, right, except at z equal to z naught, yeah, which would be not the case here. You see, around 0, yeah, there is no neighborhood which does not contain any 0, right? No matter how small the neighborhood you choose of length epsilon, you can find infinite number of zeros inside in this case. But here it cannot be, because by continuity you know that if this is not 0, then it will not be 0 in some small neighborhood around z0, right? This also is not 0 in the small neighborhood around z0 except at z0. So the product, this times that, will have no other 0 in some small neighborhood of z0. So this has no accumulation point of zeros. Okay. So this is another way to say that the zeros of analytic function are isolated. So they are not accumulation points. So they are isolated, which means around a 0 you can find a small neighborhood such that it has no other 0 in that neighborhood. That's what you mean by isolated. So zeros of analytic function are isolated. Okay. Now, what about the poles? Again, so we will again consider so the singularities. Now, let's look at the singularities, and I will only talk about the isolated singularities. Isolated singularities. Okay. So let's suppose a function f has a singularity at say some point z naught. Okay. So I finished the discussion of the zeros. Now I'm discussing a different thing. The singularities now. So if it's isolated singularity at z0, that means I can always find a neighborhood around z0 where function is analytic everywhere except at z0, right? That's what it means. That means I can use a Laurent series, because I can take a second circle as a small circle around it, inner circle, and the outer circle is that, and then I can go through the Laurent series expansion, right, for any z inside here. So in general, I can make a Laurent expansion here. Laurent expansion, which will be valid all the way for z close to z naught, because this inner circle I can make as small as I wish, right? I can take, because we are saying that it's analytic everywhere except at Z0. So this circle I can take as small as I wish. So the Laurent expansion, which will be of the form, so let me write it like this: an z minus z naught to the n for n equal to 0 to infinity, plus then b1 over z minus z0 plus b2 over z minus z0 square, and so on, right? I think I think this is what is called d minus 1, right? d minus 1, dn, d minus 2. And you remember the dn's which we entered in the Laurent expansion, and so on. It will go on like this, right? Okay. Now suppose that suppose for a particular function it happens that some d minus n is not equal to 0, but everything higher than that, meaning d minus n plus 1, d minus n plus 2, etc., everything, all of them are 0. Okay. So there is some, so d minus 1 will appear here, right, in the nth pole or nth power here. But what we are saying is that beyond that there is no other term, because everything else is 0. You're saying, huh? Suppose it happens. Okay. In that case, again it's a definition now, you say that this function has nth order singularity. It's called nth order pole. Then you say that such a function has a nth order pole at z equal to z naught. Okay. I mean, the lower one may or may not be 0. That's not important. Important point is that the worst singularity. I mean, after all, the higher the power is down denominator, there's worst singularity, right? Because when you take z goes to z0, this blows up worse and worse as you increase the value of n here, right? So what we are saying is that the worst way of worst divergence is that it goes like nth power, but nothing more than that. That is what we are saying. Not, all the higher terms are 0. So this is the worst singularity. So nth order pole means that is the way it diverges. At that rate it diverges as you approach z z naught. That's nth order pole. Okay. Was there anything else I had to say? Yeah. Again, another definition. So if there is a function which has isolated singularities, and not only that, those isolated singularities are such that it has an nth order pole, because I mean it could also happen that in fact all these coefficients are non-zero, right? That could also happen. I'm saying that let's consider the situation where not all the coefficients are non-zero. Okay, there is a highest singularity where up to which the coefficients are not 0, but everything else is 0. Okay, in that case you say nth order pole. If all the coefficients are non-zero, then it is called then you say the function has an essential singularity. It's a very bad singularity if all powers are non-zero. So if all d minus n's for n, I mean n equal to 1, 2, up to infinity, I mean infinity meaning arbitrarily high number, is not 0, then you say that the function has an essential singularity. It's a very bad singularity. At z equal to z naught. In fact, in this entire course, we are not going to talk about this case at all, essential singularity. We will be only talking about nth order pole, which means there is a finite value up to which d minus n is not 0. Beyond that, it's all 0. Okay. When something like that happens, then you say the function is meromorphic. Okay, function is meromorphic. So in such case, not in this case, not the essential singularity, but in this case, you say this function is meromorphic. So this is some definitions. These essential singularities are really bad, because I mean what happens is that if all these coefficients are non-zero, then you can prove that I mean even in this tiny neighborhood around z0, if you look at this the function f of z can take any value in the entire complex plane. It can become any complex number inside in the smallest neighborhood. No? Take any small neighborhood, right? And you see what are the values of the functions at different points in this neighborhood. You find the values of the function sweep the entire complex plane. I mean, it can be any value, you know, or it can be arbitrarily close to any value. So which means it's highly fluctuating. I mean, it's a very wild fluctuations in the in the neighborhood. So it's a very bad singularity in these cases. Yeah, it's okay. I mean, essentially, you can see that. I mean, if you look at, if you go to the polar coordinate around z equal to z0, so if you write in the polar coordinate z minus z0 equal to r times e to the I theta, okay, then you see that you get, if you have all possible powers here, you have singularities of the type 1 over r to the n times e to the I n theta, and as theta goes around, it oscillates very violently, because for larger and larger n. Right? When theta goes from 0 to 2 pi, you see it goes n times, right? This wave. I mean, after all, these are e to the I n theta is cosine n theta plus I sin n theta. They are trigonometric functions, no? So when theta goes from 0 to 2 pi, this n theta goes from 0 to 2 n pi, which means there are n oscillations, no? So it's wildly fluctuating, no? And since the magnitudes of them are also diverging 1 over r to the n, as r goes to 0, you can get this huge, I mean, values which are oscillating rapidly, no? So it's a very wild functions. So anyway, I will not be talking about this at all. There is a theorem which is proven here. This theorem, which this statement that I made, there is a wild fluctuations around, but I will not discuss that, because I am not going to use it anyway. Okay, so now what else I have to do here? Zero sum. Okay. Now I'll prove a very important theorem, and then we can stop. Actually, I wanted to do two things more, but we'll see. So the theorem of residue. This is very, very useful. This is the thing that we will be using mostly to evaluate the integrals, definite integrals. So theorem of residues. Okay. So you know that, I mean, of course, if a function was analytic everywhere, right? Okay, let's consider the following thing. I have some point z0, and I consider some contour around it, some contour c, and I just consider this integral. Let me see, the 1 over 2 pi I is included in the definition. Yeah. So I consider 1 over 2 pi I times the integral of f z prime dz prime, where you have this contour c, which encircles this point z0. Okay. Now, if the function was completely analytic here, then by Cauchy theorem, this is 0. Right? Because it's a closed contour, right? It's a closed contour. It will be 0. So if it is going to be non-zero, there has to be some singularities inside. Okay. Again, as I said, I will be only considering isolated singularities, and that too of the non-essential type, the meromorphic type, which has a finite order pole. So let's suppose that inside this there is only one singularity, z0 at z0, and everywhere else it is analytic. Okay. Then, I mean, this contour, if at all this is non-zero, it must be coming from this z0. I mean, the fact that this is singular at z0. Otherwise, Cauchy theorem says it is 0. Okay. So this quantity is, by definition, is called the residue residue at z0. Let's see if that is the way it's defined. Residue of f z0. So residue of f at z0 is by definition this quantity. Okay, the RES for residue. Huh? So as I said, so again, what is the picture? I am saying that z0 has only a singularity, it's an isolated singularity, and there is no other point which has, where it is singular. So this contour integral is going to give something, maybe 0, maybe not 0, but whatever it is by definition called residue of this function f at z0. That is what. So now let's try to calculate this. Yeah. So I mean, let's consider the following. So we said this function, I mean, it has singularity, means it has some pole, right? Let's suppose there's an nth order pole. Suppose, so I want to evaluate this, what it is. Huh? So suppose the function f has nth order pole, has nth order pole at z equal to z0. What it means is that in the Laurent expansion, the worst singularity will be 1 over z minus z0 to the power of n, right? So I can take out 1 over z minus z0 to the n outside. Okay, then it will look like d minus n plus d minus n minus 1 times z minus z0 and so on. Right? That's what it will look like. Right? If I take out, I erase the Laurent expansion, but I mean this is the worst singularity. Once I take that out, everything else will be regular with z equal to z0. So there will be an infinite series here, which will be again is convergent. So it will define to me some analytic function, right? So this will be of the form 1 over z minus z0 to the power of n times some analytic function. This whole thing, this series will define to me some analytic function. Okay. So now I want to compute this quantity here. I mean, I substitute this f of z prime there. So this once I recognize like this is 1 over 2 pi I. Again, since d minus n is not 0, okay, that means we are saying that this h of z0 is not 0. So again, with the h of z0 not equal to 0. So 1 over 2 pi I and the integral 1 over z prime minus z0 to the power of n times h of z prime dz prime, sorry, dz prime. That's the integral, which is what? Now since you see h is an analytic function, but again this gives you a derivative. This is I mean there was this formula for the derivatives of an analytic function, right? So this is nothing else but factorial, what is it, factorial n minus 1, is it? Yeah. So this gives you 1 over factorial n minus 1 times n minus 1 as a derivative of the analytic function h of z at z0, right? But again, remembering that h of z, I mean this was f of z, right? So the relation between h and f, you see that this is the same as 1 over factorial n minus 1 dn minus 1 over dz n minus 1 z minus z0 to the power of n times f of z evaluated at z equal to z0. So you take n minus 1 derivatives of this quantity and then evaluate that at z equal to z0. So this is the recipe for a function which has nth order pole at z0. Okay. But on the other hand, directly from this definition, you see this is nothing else. This by definition is the d minus 1 coefficient of the Laurent series. right? I mean, remember the dm was 1 over z prime minus z naught to the m plus 1 f z prime dz prime 1 over 2 pi I, right? So if you, I mean, here there is no power of z prime minus z naught. So if you put m equal to -1, this disappears, and that's exactly that. Huh? So there are two ways of thinking about it. This residue is the same as d minus 1, right? Or equivalently, you can think of it as this calculation. The two answers, of course, will give the same answer, result, of course. Okay. So this is the residue. Okay, here I discussed the situation where I have just one singularity. What happens if there are many singularities? Suppose there are several points here where there are singularities. Okay. Then the result of this integral, so let's say z naught prime, z naught double prime, at all these points there are singularities. Okay. Then this result will be the same as the sum of the residues of individual points. Why? Because again you can deform this contour, right? You can make it like this, write it like that, and then I mean you can deform this contour into this, right? Because in the rest of the places it's analytic, so you can deform it. So it will just become the sum of the residues. So that's the rule in fact. So integral of any analytic function in any contour, closed contour, is equal to the sum of the residues at the singular points. Okay. And that is what will be useful eventually in computing various integrals. Okay. There was I need to prove one more thing, and then you'll be set to, you'll be ready to evaluate a lot of complicated integrals. So, okay. So let's me motivate. But is there any question here? This was quite straightforward, I think, right? This was pretty clear, I suppose. I mean, it was very easy, right, in some sense. Right? This was just a definition of the first Laurent coefficient, and this is another way of doing the same thing. The same. Right? You can do either way. I mean, sometimes it turns out that this is more easy to do. Sometimes it turns out that's more easy to do. No. All right. So now the point is that what we will do, how we will use this integral, is the following. I will in fact give you some example actually. In fact, one of the examples which is done here. Suppose I want to compute an integral like this, definite integrals. These are definite integral. Definite integral. You're right. I mean, so, or let me try to do something else maybe. Okay, let's try to do that. So, I mean, suppose I want to do an integral of this type, dx squared dx, x squared plus. Okay, this you can also do without using these tricks, but just to show you how easy it is to using this residue trick, you can integrate. This is just an integral from, for example, 0 to infinity, or equivalently minus infinity to plus infinity, because after all it's an even function of x, so you can as well extend it to. So what I'm doing is I'm trying to integrate over. So this is my x. X is this direction, and I want to integrate this object here. Now, if you think of, instead of x is a real number, right? So think of just replace x by z, z squared dz, z squared plus 1, z squared plus 4. And so from the point of view of a complex thing, all I'm doing is I'm integrating over a contour where the contour is along the real line, right? However, it's not a closed contour. I mean, in order to use residue, you need to have a closed contour, right? So there are various possibilities. Well, I could say integrate from minus capital R to plus capital R, and then go like that, and then take a semicircle of radius capital R, right? So this radius is capital R. Okay. And so now it becomes a closed contour. and then evaluate this whole thing and then take the limit r goes to infinity in the end, right. So what will be, so of course one part of the contour is just that integral, but the other part of the integral is a semicircle of infinite radius. Okay. Now if it happens that somehow you can show that that part of the integral vanishes in the limit r goes to infinity, okay, which is not surprising because you see when z is large value of, so on this semicircle z is r times e to the I theta, right. So how many powers of r will appear in the numerator and denominator? Here you have r square, from there is a, from the change of, I mean dz will be r dz will be I r e to the I theta d theta on this circle, semicircle, because r is fixed, what is changing is theta only, right. So it's theta that you are integrating from 0 to pi. So 1 power of r from here, 2 powers from there, but that from down you get 4 powers. So clearly r goes in capital R going to infinity, this will go to 0, right. So in this case you can extend the contour to make it a closed contour, because anyway this part of the integral gives you 0, right. Okay. So now from the residue theorem, I mean the only thing that you, this integral will just simply give me 2 pi I times the residues inside this semi disk, right, wherever there are singularities. So now look at where are the singularities here. One singularity is z equal to plus minus I, right, because when z equal to I mean I or plus or minus I, z square is minus 1, so this becomes 0, or z equal to plus minus 2I, because 2I square is minus 4. So you have the singularities here in the, along the imaginary axis at plus I, plus 2I, and minus I and minus 2I. So if you are integrating over this upper semicircle, then the residues will, I mean the only thing which matters is the singularities inside the contour, right? Outside you don't care. So just compute the residues at these 2 points, and that gives you the answer to this integral, right. So it's a much easier calculation rather than actually explicitly carrying out the integral. Of course this is still a very simple integral, you can do it explicitly, but still I'm just trying to show how useful it is using this residue. Several times it's not just such simple functions. There is another example I give you. I mean we can work it out next time, we can work it out explicitly what the answers are, but you see I'm just telling you the procedure, how you will use this, all this thing too. Now it's a much more complicated integral is this integral, which again I will do next time in detail, but I just want to give you so take another integral which is 0 to infinity of sine x, sine the trigonometric function sine x divided by x dx. This is a very complicated integral. I mean I don't think it is, I don't know of some simple way of doing it, I mean directly, no? But I mean by using residue theorem you will see how you can work it out. So so what you do here is okay, this is a slightly, it's not exactly, there is some more tricks involved in this, but the essential point is again, after all sin x is the same as e to the ix minus e to the minus ix over 2I, right. Remember that was a formula for the sine. Cosine was the sum of the 2 divided by 2, because e to the ix is the cosine x plus I sin x, right. So you take this plus e to the minus ix and then add and subtract, you get cosine and sine, right? And then put it back here. So then there are 2 terms. First of all, let me point out this thing. You have 0 and infinity. At 0 you may say that, well, there is a singularity here, but it's not, because sin x also vanishes, right. So this is well defined at x equal to 0. So it's as a trick, what we will do is we will integrate from some small r or epsilon, let's say, to infinity, or again infinity, let's make it capital R, right? So this is some epsilon up to capital R, and then after doing this integral we take the limit epsilon goes to 0 and r goes to infinity. There is no problem with this, because anyway we know that at x equal to 0 actually there is no singularity. So, this limit is well defined, there is no problem with this. Okay. But now substitute this here, there will be two terms. One will be e to the I x over x, okay, there is a 1 over 2 I, right, dx from 0 to infinity, and then there will be another term which will be e to the minus I x minus e to the minus I x over x dx, 0 to infinity, right. I mean not 0, sorry, epsilon to infinity and epsilon to infinity. And then at the end r, capital R, and then take the limit epsilon goes to 0, r goes to infinity. You see, r goes to infinity, again you may wonder, is there a problem with this? Huh? But actually again there is no problem. I mean, if sin x was not there, then dx over x diverges because it's a logarithm, right? Integral, and then log of infinity is infinite. But sin x, because it oscillates, I mean there's a plus and minus, so there are cancellations. So this is well defined actually, although it's not obvious at this stage, but we will see the integral will be finite. Okay, so this is what it is, but now I can change the variable here x to minus x, so the integrand looks the same. Here change the variable x going to minus x. Okay, so this makes it plus. Dx over x again remains unchanged because this picks up a minus, that picks up a minus, but the limits will become minus, right? So this will be minus epsilon to minus r. Okay, so which again I can write it as, absorb this sign, I mean this sign, make it minus capital R to minus epsilon. Okay, so now this integral looks like this. I have 0 here, epsilon here, minus epsilon, minus r and plus r. Okay, and integrand is the same. So basically what we are doing, we are taking the same integrand, integrating from here to here, okay, up to this point, and then from here to there. So arrow is the same direction. Again, it's not very useful at this stage, but what you do is again you make it into closed contour. Draw this big semicircle of radius capital R, right? And here, so go like that and go like this here. Now this integral you can perform explicitly, because after all this is a small epsilon. Epsilon is small. So you can use, I mean, expand the exponential. Okay. So this you do explicitly, this integral. It's very easy to explicitly carry out the integral. So what we are seeing is that this plus that this whole integral is equal to the residues inside of this function. But this function has no singularity inside here, you see. So what it means is that this integral plus that integral is equal to that integral plus that integral. Okay, that's what we are saying. Now we can show that this integral, I mean somehow we want to show that this integral is vanishing, otherwise it's difficult to calculate it. So that is why I need to prove a lemma, which again I will prove next time. In some sense it is easy. See, you can see that see the integrand is e to the I z divided by z, right? It just replace x by z. Integrand is e to the I z divided by z, right? Now this has no singularity inside here, so it has no residue. But look at this integral. At this integral, here you see there is a imaginary part of z is positive, right? After all, I mean on this circle, the z is capital R times e to the I theta, which is cosine theta, plus I sine theta, right? Z is R, capital R times e to the I theta. I just write like this. This is the imaginary part, which is capital R times sine theta. Sine theta between 0 and pi is positive. Okay, so it has a positive imaginary, which is already clear. Its imaginary part is positive, right? But it's a positive part which is multiplying capital R, and capital R is large because eventually I'm going to take capital R to infinity limit, right? So you have a positive imaginary part. So you look at this R, I sine theta, and there's another I square is minus. So you find there is something like e to the minus r sine theta, right? For r goes to infinity, exponentially suppressed. Okay, so it will not give any contribution. So the lemma that I want to prove is that this will not give any contribution. I mean, you have to be a little careful and so on, but intuitively you see why this doesn't give a contribution. Exponentially, it is exponential suppression, and for the same reason, it was important that I went along that contour. You see, there were two ways of doing it. I could have also done down, right? That will not be meaningful because then this would be negative. I mean, sine theta will be negative down here, so it will be exponentially blowing up. So you can't use, you cannot do that. I mean, it will not give you any meaningful answer if you try to do that. So this is a lemma which I will start. Next time I will start with that. It's Jordan's lemma, which we need to prove, because in many applications there will be exponential functions will appear, and there you need to know which way you should deform the contour, whether you should deform up or down, you know, etc. So I'll prove that, and then we'll consider several examples, how to evaluate this integral and many other integrals, and so on.